Hello everyone, my name is Nishant Kumar and today I'll be presenting to you our work on CrypTFlow, Secure TensorFlow Inference. This is joint work with Mayank Rathi, Nishant Chandran, Divya Gupta, Asim Rastogi and Rahul Sharma, all from Microsoft Research India. The problem that we are trying to solve over here is that of secure machine learning inference. Consider a hospital that has a proprietary machine learning model for respiratory diseases and a user who has his medical data and who is interested in using the machine learning model to do inference on his medical data. Now there is a privacy tension here because the hospital doesn't want to give out its machine learning model since it is its own proprietary model, and the user doesn't want to give out his medical data because it is his private data. Now, cryptography provides us a way to resolve this tension with the two parties running a cryptographically secure protocol amongst themselves, at the end of which the user learns the disease prediction and provably none of them learn any information about the other party's data. The cryptographically secure protocol that I refer to over here is a primitive that in cryptography is referred to as Secure Multi-Party Computation or MPC. So what is MPC? In MPC, there are a bunch of parties with private inputs who are interested in computing the function f on their private data. For example, consider here three parties P1, P2 and P3 with private inputs x1, x2 and x3 who are interested in computing the function f on their private data. With the help of MPC, the parties can run an interactive protocol amongst themselves at the end of which they learn the function output and nothing more about the other party's data. The theory of MPC had been developed way back in the 1980s with protocols like Gauss-Gerber circuits and GMW, but it is only recently that some of these protocols have become efficient enough that they can be used in practice. While there has been a plethora of works on using MPC techniques to solve the problem of secure machine learning inference, prior work in this area has lagged along three different dimensions: usability, scalability, and security. Let me elaborate on each of these one by one. In terms of usability, the crypto protocols that are used for MPC work with low-level representation of the function they are computing. This is usually in the form of arithmetic or Boolean circuits, and this makes it hard to code or debug large applications. The other main issue in terms of usability is with float to fixed point conversion. The ML models that we are talking about over here work with floating point arithmetic, while the crypto protocols that we want to use have better efficiency working over integer rings. We then need to encode the floating point numbers into integer rings using finite bits of precision and define an arithmetic over that. This is what is known as fixed point representation. Prior works in the area of secure machine learning inference have resorted to a manual process of converting from floating point to fixed point. While this can be done for one or two small benchmarks, this quickly becomes intractable for large benchmarks and needs to be repeated for every new benchmark. In terms of scalability, prior works in this area have worked with small datasets and models. And when I say small here, I mean datasets like MNIST or CFAR, which have between 10 to 100 classes, and the networks that work over them have less than a million parameters. We would like to ideally work with datasets that are at the scale of ImageNet, which has around 1,000 classes, and the networks that work over it have millions of parameters. For example, we would like to ask if we can do networks like ResNet 200, which works over the ImageNet dataset and which has around 65 million parameters. The third dimension is that of security. Prior works in this area have mostly worked in the weaker semi-honest security model, where it is assumed that the parties will be following the protocol execution honestly. Instead, we would like to ask if we can do the stronger model of malicious security, where even if the participants arbitrarily deviate from the protocol, the security of the protocol still holds. With these issues in mind, we set out with the following goal. Consider a developer who is interested in the MPC protocol implementation for the function f. Ideally, he should only have to represent f in the most natural framework for expressing it, and then push a button and get a secure and efficient MPC protocol implementation using some crypto and compiler magic. For machine learning applications, one of the most natural frameworks for expressing these computations is TensorFlow, and which we consider in this work. We also want several things from the compiler. The compiler should be user-centric and error-proof, meaning it prevents the developer from committing security mistakes. It should hide all the cryptographic details from the developer so that the developer remains oblivious of these and just writes vanilla code. We also want that the protocols output by the compiler should have good performance and should provide the flexibility of choosing between both semi-honest security model and malicious security model. And this is exactly what we get in this work with CrypTFlow, an end-to-end system for secure machine learning inference. To tackle problems along the three dimensions that I had talked about earlier, CrypTFlow provides three components. For usability, CrypTFlow provides Ethos, which is a compiler from TensorFlow inference code to semi-honest MPC protocols. For scalability, CrypTFlow provides Porthos, which is an MPC protocol geared towards neural network inference applications. For security, CrypTFlow provides RMS, which is a general technique of converting any semi-honest MPC protocol to a maliciously secure protocol, assuming a secure hardware that provides the guarantee of integrity of computations. And with these three components in place, we are able to achieve ImageNet scale secure neural network inference for the first time. And we do this without losing any accuracy compared to the plain text. To give you a sense of some performance numbers, here I have two networks which we consider for our benchmarks. ResNet 50 and DenseNet 121, both of which work on the ImageNet dataset. While ResNet 50 is an ImageNet Challenge winner from 2015, DenseNet 121 is a CVPR 2017 Best Paper Award winner. In the semi-honest security model, in the LAN setting and on commodity hardware, we are able to run both of these in around 35 seconds. While for malicious security, we are able to do this in the same setting with a less than 3x overhead. So now that you have a good overview of the complete system, let me move on and give you some more details about Ethos and RMS. In this talk, I'll not be talking more about Porthos, but I request you to please check out our paper for further details on that. So recall that Ethos is a compiler from TensorFlow inference code to MPC protocol implementations. The input to Ethos is then the TensorFlow code, and the first step in the compilation process is the metadata generation phase. This metadata consists of two information, the TensorFlow graph itself and the shape information of all the tensors involved in the computation. This is followed by a compilation to a high-level intermediate language called HLIL. HLIL consists of a sequence of function calls and with support for floating point tensors. For example, consider logistic regression and consider this small snippet of code written in TensorFlow that performs that. Here you see a W times X plus B being performed and an argmax over that to get the prediction. The metadata for this TensorFlow code would then look like this. On the left side, you see the TensorFlow graph itself, and on the right side, you see the shape information of all the tensors involved in the computation. The HLIL code that would be produced for this would then look something like this, a sequence of function calls over the floating point tensors. The next step in the compilation process is the floating point to fixed point conversion. Recall from our discussion earlier that machine learning models work over floating point arithmetic, whereas crypto protocols have better efficiency working over integer rings. The encoding of the floating point values in these integer rings using finite bits of precision is what is known as the fixed point representation. Concretely, consider the real value r. Its fixed point representation would then be given by floor of r into 2 power s, where s is a parameter known as the scale factor and which determines the number of bits of precision chosen after the decimal point. Prior works in the area of secure machine learning have resorted to a manual process of converting from the floating point to the fixed point representation. Ethos performs this work automatically. The challenge in doing this is to choose the right value of the scale factor. Too high a value and this can lead to an overflow and the loss of the most significant bits leading to a drop in accuracy. Too low a value and that means the number of bits chosen after the decimal point are limited and this will again lead to a loss in accuracy. Our approach to solve this is to consider the scale factor as a hyperparameter and use the validation set to tune and find the right value of it. For example, here I have a graph that shows how the accuracy varies as Ethos performs a sweeping across multiple scale factors. For our benchmark network of ResNet 50, the constant line at the top that you see is the floating point accuracy of 76.47. As Ethos performs a sweeping across the scale factors, it finds that at scale factor equal to 12, the accuracy peaks and is equal to 76.45. It then performs a conversion taking s is equal to 12. Once the floating point to fixed point conversion is performed, Ethos compiles HLIL to a low-level intermediate language called LLIL. This is a C-like imperative language for expressing the computation. The logistic regression example that I had shown earlier would then look like this in LLIL, assuming Ethos chose a scale factor of 15 for performing the conversion. The design of LLIL is modular with an interface for plugging in different crypto backends. The observation here is that TensorFlow operations can be divided into two categories: non-data manipulating operations and data manipulating ones. Non-data manipulating operations are TensorFlow operations like squeeze, pad, transpose, etc., which move the data around without actually changing any existing value. Data manipulating operations, on the other hand, consists of operations like matrix multiplication, ReLU, pooling operations, etc., which change the value of the incoming tensors and perform an operation over them. To reduce the load on the crypto backend, Ethos provides an LLIL library which takes care of all the non-data manipulating operations. The crypto backend then only has to implement the data manipulating operations, which are far fewer in number than all the operations that are supported by TensorFlow. To demonstrate the modularity of LLIL, we currently have two backends implemented into it, ABY and Porthos. ABY is a two-party backend from NDSS 2015, while Porthos is our own three-party backend. The final step is then the compilation of LLIL to the crypto backend of choice. And that completes the compilation by Ethos to the MPC protocol. The design choice of having two intermediate languages, HLIL and LLIL, allows us to perform various standard data flow and compiler optimizations. Please check out our paper for more details on this. Finally, we note that for our benchmark networks with all the compiler optimizations, our compilation times remain within a reasonable 40 seconds. So that was Ethos. Now let's move on and talk about RMS. Recall from earlier that MPC protocols can have two levels of security. Either the weaker semi-honest security, where it is assumed that the protocol participants will be following the protocol honestly, or the stronger model of malicious security, where it is assumed that the participants can arbitrarily deviate from the protocol. The approaches to get malicious security can then be divided into two categories: crypto-based or hardware-based. Crypto-based approaches to MPC design cryptographic protocols for the same, and in practice, for semi-honest security, they are able to get reasonable performance. But for malicious security, while specific techniques for specific protocols can have reasonable overhead, generic techniques that work over arbitrary protocols are very expensive and have a large overhead. In the hardware-based approach, consider two users, Alice and Bob, with inputs x and y, who are interested in computing the function f of x, y. Consider another user named Charlie who has support for secure hardware like Intel SGX. The secure hardware provides two guarantees, a confidentiality guarantee and an integrity guarantee. The confidentiality guarantee makes sure that the runtime data remains secret, and the integrity guarantee makes sure that the code or data cannot be altered. Alice and Bob can then send their inputs x and y to Charlie, who computes the function f of x, y inside the secure hardware and sends the output back to Alice and Bob. While such hardware-based approaches are faster than crypto-based approaches, these typically suffer from side channel attacks. For example, foreshadow, meltdown, and plundervolt, which is another work appearing in this symposium, are attacks against Intel SGX. This is where RMS comes in and tries to combine the two approaches. As we have seen, crypto-based approaches have reasonable performance for semi-honest secure MPC protocols, whereas hardware-based approaches suffer from attacks that break the integrity and confidentiality guarantees. We then assume a secure hardware that only provides an integrity guarantee and combine this with the semi-honest secure protocols to get RMS. With a combination of these two techniques, RMS is able to get malicious security from any semi-honest secure protocol, assuming a minimally secure hardware that only provides the integrity guarantees. Let me elaborate now on how exactly RMS combines the two approaches to get malicious security. Our starting point is a semi-honest secure protocol, and what we desire is a maliciously secure protocol. Recall that In semi-honest security, it is assumed that the participants in the protocol will be following the protocol honestly, whereas in maliciously secure protocol, the participants can arbitrarily deviate from the protocol. If then there were a mechanism by which we could force the parties to follow the protocol specification, then we could convert the semi-honest protocol to a maliciously secure protocol. This is where we use the secure hardware providing integrity guarantees and use it to ensure that the parties are doing a faithful execution of the protocol. I refer you to our paper for more details on exactly how this is done, but at a high level, all the participants in the protocol run a secure hardware and in initial phase establish trust of the code running inside the hardware by a process called attestation. They then run the semi-honest secure protocol, but with messages that are signed by the secure hardware, providing integrity guarantees. The signing ensures that the participants are doing a faithful execution of the protocol, and that is how we are able to achieve malicious security. For our prototype implementation, we use Intel SGX as the secure hardware of choice. There are several challenges that come with using SGX. First, porting highly interactive MPC protocols to SGX comes with several implementation challenges. Secondly, the ImageNet scale inference tasks that we are trying to run inside SGX are memory and compute intensive and lead to their own set of implementation challenges. I refer you to our paper for more details on how exactly we overcome these challenges. But with both these challenges overcome, we are able to scale RMS to networks as large as ResNet 200 with an overhead that is less than 3x of that of semi-honest. In summary, we present to you CrypTFlow, which is an end-to-end system for secure machine learning inference. To do this, we built three components: Ethos, Porthos, and Aramis. Our paper and code both are available online, and I request you to please check these out for more details. Thank you.